recording. Let me start sharing my screen. Let me go in. Oh, this is not your class. This is your class, part of it. Let's see. Oh dear. We had said that the exam for chapter 8 is going to be due from after class time today until Sunday at 11:59. The homework and activities 2 and 4 are also due today. Activity 5 is extra credit. Just reinforcing in terms of that, the activities, if you don't have an activity manual, are in this folder, but also in, whoops, take that back, I lied. There is a folder here to submit your work. And so there should be a place to submit your work for homework 1, a place to submit your homework for chapter 8 activities, and a place to submit your work for that extra credit activity. Going back, there is also a separate folder for the tests and for the chapter, oh, this touch screen and I aren't getting along today, I'm sorry. For the chapter 8 tests, there will be, the first link is where you will find the test questions. With the test questions, for each question, there is a place where you can type your answer in, or if it's a short answer, put your answer in. But again, if you don't want to type them in, and for everything, I really do want to see your work. When you do your work by hand, you're going to submit those in this drop box here. I think the other day we went through how, I mean, if you want to use a scanner or something, that's fine. But personally, I find it easiest if I open that on my phone. Blackboard, if you're using an Android, the Blackboard app, if you're using an iPhone. And when you click on that, submit your work, there's a place where your phone opens up and you can just take pictures and submit them. What I didn't say the other day, initially when my phone opens up, it's kind of in selfie mode. I take it out of selfie mode so I can just take a picture of my work. There's one person in one of my other classes that always takes a selfie of herself holding her work up in front of a mirror. It's easier if you take it off a selfie mode. It's easier to read if I just get a picture of the paper. Because some of the questions ask you to graph, I would like it if you could possibly do those on graph paper. This link above is a place where you can download a sheet of graph paper. If you have another app that you use to print out graph paper, fine. If you have plain old graph paper at home, you can use your own graph paper, but take a picture of the graph on graph paper if you could. If that's a problem for anybody, let me know. Does anybody have questions about how you're doing the tests? And again, over here it says availability. This item is hidden from students. Let me just double check. That's not going to show up for you. But if I go here and hit edit the test options, if I am not mistaken, I have that set so that the test will appear for you. This should fill in. Yeah, it did. It should appear for you today at noon, so after class is ended. It's a time test. You have 60 minutes for it. If it takes you longer than 60 minutes, you can still do it, but it's going to mark it as late. So, any questions on any of this? Any questions on anything that we did in chapter 8? If not, I'm going to change my mind. I'm going to go back into Blackboard once more. And hopefully it's all right for everybody in terms of learning modules and content. Over here where it says class notes and recording, I only have one in Chapter 8. I only have one file for class notes because I don't know if you noticed, every time we took notes, I went back to the same OneNote that I was working in and added on. There's a separate YouTube for each class, but there's only one folder for the notes. And if I go back into learning modules and content, you'll see that in the notes outline, that's where you're going to find what we're going to start with today, those Chapter 9 notes. And when I uploaded them, the Chapter 9 notes into OneNote, in addition to those notes, I did upload, if you look over here on the side, the Chapter 9 activities. With Chapter 9 activities in the course outline, I have activities 1, 2, 3, 4, and in the course outline, I also have activity 7. Activity 7 is it's quite involved. And so activity 7 tries to pull together what we did in Chapter 8 with coordinate geometry with some of what we're doing in this chapter with geometry. But because it is quite involved, and I know that between the activities and the homework, I give you guys a lot of work. If anybody's interested, that one will be an extra activity. It'll be extra credit. And if you look at the course outline, there, just like last time, there's a day at the end of the chapter that I have set aside to work on the activities. If you want to work on them ahead of time, it's fine. But I will be asking you towards the end of the chapter to work on the activities together again in small groups. And where was I going with that? And also, hopefully there's a day at the end, like last time, to do a little bit of reviewing and answer questions that people might have on the homework. Before we start looking at this new chapter, does anybody have questions about anything at all from the older things from Chapter 8? Jess, I got you. Any questions? If not, let's see if I can make this a little bit bigger. There you go, just a little bit bigger. We're going to start looking today at geometry. And I'm one of those people who really, really likes geometry a lot. Is there anybody in class who in high school took geometry and you did like all of the geometry proofs, the statements and reasons and all of that stuff about triangles? That was when math became alive for me. That was when I began to really, really like the subject matter, because all of a sudden it became much more reasoning and thinking, and the idea that if you understand something and know the why of it, there is no need to memorize. And I know that the high school that I went to, I was very blessed. The first geometry class that I took, before we started doing those proofs, I had a wonderful teacher who pointed out the fact that we're going to spend a lot of time doing, at that stage, we spent a lot of time doing geometry proofs, and you had to make statements and you had to make reasons. And she said, yes, in real life, you will probably never be asked to do anything like this, but it's the one place where in your secondary career where you learn how to construct a logical argument. The fact that, statements must come in order to make sense. The fact that that you cannot say something unless you can justify it with a reason. Hopefully that level of reasoning skill carries over to every other course you take, every paper you write, every outline you make. And it's more the thinking skills than the triangles. And those thinking skills are taught in a math class in that way because in terms of triangles, it's black and white, as opposed to in terms of things that you might do in writing a paper using those skills in something like a history or an English class. It's not so black and white. There are shades of gray. And so it's easier to teach those skills with things that are very factual as opposed to things that are interpretive. And I just thought that that was a wonderful spin that was put on geometry for me. And I don't know if many students get that, but anyways, that's the old lady and me ranting and raving. So how much geometry have you folks taken? Have any of you taken a geometry class in high school?
Yes.
And did you have to do those geometry proofs?
Yes.
In this class, we're not going to necessarily do proofs, but on this test, there is at least one question where you don't have to do statement and reasons, but you have to kind of in a paragraph form, explain why with given information something must be true. And we will look at a couple of examples like that towards the end of this chapter. Towards the end of this chapter, one of those last homework problems is actually asking you to in that way justify and therefore prove the Pythagorean theorem, which is kind of cool. But I digress. We're going to start looking at, in the first couple days I know are tedious for folks because it's very definition-y. Rather than having us write out the definitions for most of the definitions, I do have them typed in, and we're going to look at more of the applications and the diagrams and things like that. But before we even do that, has anybody ever heard the idea that a definition is good if it only uses previously defined terms? The idea that a definition only makes sense if you know what the words in the definition mean. And so if I define this, the words that I use to define it, I should have defined already someplace else. The words in those definitions I should have defined already someplace else. And we can keep on backtracking. And so somewhere along that line, you get this idea that my basic building blocks, what I start with, are going to be considered undefined terms. And so the first thing that's considered an undefined term that we will describe but not define is a point. And we're going to think of a point as a location in space. We show a point with a dot, and we usually label them with an uppercase letter. So this dot here might be point A. And then we're going to look at a line being an infinite collection of points. They're kind of like strung together. Usually we think of them as being straight. USUALLY. And so I'm sure that everybody's seen a line drawn. It's infinite. So if it's a line, it's important that we put these arrowheads on the end. And this line should be made up of an infinite number of points. Those of you who took 108 looked at the relationship between the points on a special line, the number line, and how every number has a point, every point has a number. Usually to name a line, I look at 2 points on the line. And so this could be referred to as line CD. And I show that notation wise by having CD and putting a line over it. I could also call that line DC and put a line over that. If there was another point in the middle, I just got to make sure that my points are in order. So I could call that line CED or DEC. Also, as you're looking at examples in the textbook, sometimes they label lines with a single script lowercase letter. So I might also refer to this line CED as line L. Idea of a line, how to label it, how to show it, how to name it, all right. If so, the next thing that we're going to look at is a plane, which is a flat surface. It's infinite in all directions. And it's made up of points. The analogy that I make for a plane is the sheet of paper that I'm writing on, the surface that I'm writing on. But in my imagination, the surface isn't just the screen that I'm writing on, but it goes infinitely in all directions. Collinear points are points that lie on the same straight line. And so up above, I could have said that C, E, and D in the example above are collinear. They lie on a same straight line. In that first page of homework, there's some questions that are really quite wordy and they look involved. Please try those sooner than later, because a lot of what those questions involve is just you very carefully drawing a picture. Please do me a favor. If a question asks you to draw a circle, don't just freehand it. Either if you have one, use a compass to draw it, or draw around something. Trace around a coin, trace around a can, trace around a cup, trace around something that's round. Don't just wing a line. Use a ruler or a straight edge to draw a straight line. Because in some of those questions, if you do the drawing right, they ask you to draw a conclusion. And conclusions could be things like the points are collinear. Or concurrent lines are lines that intersect at the same point. So over here, and I have to apologize, I'm making a liar out of myself because I am not using a straight edge, but with a touch screen, that's difficult. But over here, I could say that lines M, N, and P are concurrent. They all intersect at the same point. And so if lines intersect, they're concurrent. If they don't intersect, and this is something that we talked about with a little bit in our coordinate geometry, they're parallel. And so over here, I could say that lines F, G, and H, K are parallel. FG is parallel to HK, but again, mathematicians are intrinsically lazy and don't like to write. And so instead of writing that word parallel, sometimes frequently you see a symbol that looks like this in between the two lines. And the symbol almost looks like the L's in the line, the word parallel. That symbol means parallel. No points in common or all points in common. And I think in coordinate geometry, we talked about the all points in common, meaning that we'll be able to say that a line is parallel to itself. A transversal is a line that intersects two other lines in two distinct points. A lot of times you see that idea of a transversal with parallel lines. This third line that crosses the other two in 2 points would be my transversal. But technically, they don't necessarily have to be parallel. I just need a third line that crosses the other two in distinct points to be my transversal. So far, so good. And I apologize, geometry frequently starts with a definition day, and I feel awful because it's me speaking at you. And I'm gonna go on the assumption that a lot of these terms you know already, but I just wanna make sure that everybody's working with the same definitions. Everybody okay so far? Can you guys hear me?
Yes.
Okay, thank you. Then next page of the notes. In terms of lines, the whole line is infinite. When we talk about a line segment, we're talking about if a part of a line between two given points called endpoints. And so over here, if this is L and this is M, this doesn't go on infinitely. It stops at the endpoints. So this would be segment LM. And notation for a segment is we draw a segment on top. When we're talking about a segment, we have no arrowheads. It's just that part. And so if I write LM like this, it means the segment. If I write LM like this without a hat on it, it means the length. And so let me draw two segments here. Let me draw NP and QR. And we're going to say that NP is congruent to QR if the length of NP is equal to the length of QR. This symbol means congruent. And when I use this congruent symbol, I'm talking about geometric figures like segments or shapes. As opposed to here without the hat on them, I'm talking about lengths. And lengths are numbers, and numbers are equal. And I'm going to scooch over to the side a little bit, and I guess we'll go in this margin. When I look at that symbol for congruent, congruent has two bars. That means equal, which means the same size. They're equal in size. And then above, there's a squiggle that's used for similar, which means that they have the same shape. And so if figures are congruent, they have the same shape and the same size, which for segments mean that they'd have the same length. So far, so good. I hope I'm not making anybody seasick moving things around on the page. I apologize. If I talk about midpoint, let's say this is ST, and I'm going to have M be the midpoint. A midpoint divides a segment into two congruent segments. So over here, if M is the midpoint of ST, it means, it tells me I'll be able to conclude that SM is congruent. Oh, I wrote that upside down. Is congruent to MT. Or I could also say that the length of SM is equal to the length of MT. And different from a segment is array. Array is a part of a line that consists all of the points on one side of a given endpoint. So I'm going to have one point and then all of the line on the other side. If this is V and this is W, when you name array, the endpoint must come first. So this would be array VW, and the symbol for array looks like array. It's an arrow, it has only an arrowhead on one side. Is everybody all right? I could not call this one WV. That would not be the name of this one because WV instead would be array that started at W and went through V in the other direction. And that's not what we're referring to. Once we know what array is, we can use rays to make an angle. I'm guessing that everybody in the room can draw an angle. How would you define an angle?
Made up of 90 degrees.
Some have 90 degrees, but not all of them. It could be 90 degrees, but I don't think this one over here is 90 degrees. What do you use to measure an angle? Don't you use a protractor? So they have different degree measures. We'll talk about measurement in a minute. We're going to officially define an angle as the union of two rays with a common endpoint. With a common endpoint. So if I look at this ray, this angle, pardon me, do you see here I've got one ray, here I've got another ray, and they both have the same endpoint. That endpoint is called the vertex, and we can use it to name. And the rays are considered the sides of the angle. And so let's say this is X, Y, Z. I could name it by the vertex, angle Y, but I can only name it by the vertex if there's just one angle there. Instead, off here on my scrapbook, if I had a picture that looked like this, and this point was A. You see, if I referred to angle A, you wouldn't know, do I mean the big one, the middle-sized one, the bottom one? So over here, I could not refer to it as angle A because there are too many angles at A. So over here, I can name this angle Y if there's only one angle with the vertex at Y. I could name it angle X, Y, Z. The vertex has to be the middle letter. I could name it angle Z, Y, X if I wanted to go backwards, as long as they're in order and the vertex is in the middle. And sometimes you see something like a number in there. I could, if it's labeled, I could also refer to that as angle 3. And when I draw an angle, it divides the plane into 3 regions. One region would be inside the angle or the interior. Well, if that's the interior, out here would be the
Exterior.
beautiful. So inside is one region, outside, exterior is the other region. What the heck is my third region? Any ideas? Can anybody see in that picture any points that wouldn't be inside the angle or outside the angle? I'll give you a clue. The points on the angle? The points on the angle are neither inside nor outside. They form the angle. So those are my three regions. Page 2, okay. If so, page 3, we're going to measure angles in degrees. That's not the only way in which angles are measured. Has anybody ever heard of an angle being measured in something like radians? If you've taken a trigonometry class, you've heard of radians. If you ever take a calculus class, everything in calculus is based on angles in radian measure, not degree measure. When I talk about measuring an angle in degrees, well, we better define what a degree is. We're going to say that 1 degree, which we'll write as 1 degree, is defined as 1/360th of a complete rotation. And so if I picture a point, usually there's one side of an angle that's considered the initial side. Usually the initial side is horizontal. It's like if I were picturing this as the origin, it's comparable to the positive x-axis. And if I were to go all the way around, it would be 360 degrees. Anything less would be a fraction thereof. So for example, I'm going to call this point B, and I'm going to pretend that this is 30 degrees. And so I would say that the measure of angle B equals 30 degrees. Because I'm sorry, I said 30 and I wrote 90. Somebody put that idea in my head, is 30 degrees. When we talk about numbers, we use equal signs and we put the little m in front to mean that we're talking about the measure. Technically, I should not write that angle B is 30 degrees because angle B is that physical thing. 30 degrees is its measure. Now, I have to apologize. This is the first time that I've taught this part of the course virtually, and it didn't strike me until just now. Does everybody have a protractor?
Yes.
Does everybody know how to use a protractor?
No.
No. Okay, so.
I don't even know how to use a compass either.
Okay, well, here's my protractor. And there's a point here, and there's a line here. And let's say I want to measure an angle. I'm going to make my angle orange. When I measure my angle, my protractor should be transparent, and I should put the point on the vertex, and I should put one side along that line. Now, when you look at your protractor, there's going to be two systems of numbering. One's going to start here, 0, and up in the middle, it's going to be 90. And then it's going to go down to 180. And the other, I want to use a different color. What color will I use? It's going to start here, 0, and go up to 90, and go down to 180. And so what you have to do is you have to look at your angle. If your angle is small, you're going to use, you want the number to be smaller than 90. If your angle is open wide, you want to use a scale that makes it larger than 90. Or what I like to say is, I want to make sure when I'm measuring this angle, get orange again, this angle, I use the scale where that side is 0 and count up from 0. Does that make sense? I apologize. I will try to, over the weekend, find a virtual protractor, pardon me, that I can put on a surface and kind of give you a better ideas as to what I'm talking about. We can classify angles by measure. A 0-degree angle actually looks like a ray. It doesn't open up at all. A straight angle instead is an angle that looks like a line with a point on it, and it measures 180 degrees. Can anybody help me with what a right angle is?
90 degrees?
It measures 90 degrees. What's it look like? Kind of like
Doesn't it
that.
have a little corner, like the little corner has like a box in it?
Right. If the box isn't there, don't assume it's right because it looks it. A right angle is always going to have that box in it. An acute angle, anybody know what acute means?
Less than 90?
It's less than 90. But we have to add something else to it. It's less than 90, but it's also greater than 0. Because if I open up like this, this would be an acute angle. And when I open up, it's a positive angle. Instead, if I had an angle and you're told that it opens down, in some instances, that's going to be considered a negative angle. And we don't want all negative angles to be considered acute. And so we're going to say that an acute angle has a measure between 0 and 90 degrees. An obtuse angle is going to be an angle whose measure is greater than 90 but less than 180 degrees. And so if I picture an angle that's open further than a right angle, but not quite as far as a straight line, it's going to look something like this. And so this angle here would be obtuse. Open past 90 degrees, but not as far as 180 degrees. These definitions, okay. Then A reflex angle is going to be an angle that's over 180 degrees. And so if I picture this being my initial side, 180 degrees would be here. And so if I picture an angle that opens further than that, so that we're going 180 degrees and then a little bit more, that would be a reflex angle. And again, congruent means equal measure, same shape. Congruent angles are going to be angles whose measure are equal. And so let's say I have over here angle C, and I have over here angle D. If the measure of angle C equals the measure of angle D, we'll say that angle C is congruent to angle D. And in a diagram, if they want you to see that two angles are congruent by looking, they're going to put the same number of little arcs on the interior. And I'm thinking, I'm not sure, I don't remember if later on this page I have this definition. And so I'm going to add the definition of an angle bisector. And an angle bisector is a ray on the interior of the angle that divides it into two congruent angles. Or the idea of something's being bisected, I'm cutting it in half. And so let's say this is the angle EFG. We'll say if we know that FH bisects angle EFG, well, if I'm dividing it into two congruent parts, I'll know that angle EFH is congruent to angle GFH. Bisector is always going to divide something into two congruent parts, two things that are equal in measure. Anybody hear of perpendicular lines?
Yes.
What do they do?
Form to meet right angles.
Form to meet right angles. Beautiful. And so let's say over here I have line L. Over here I have line M. And let's put some points here. Let's call this J, K, L. If line L is perpendicular, and the symbol for perpendicular is that upside down T. So if line L is perpendicular to line M, I'll be able to say that angle JKL is right. Or I'll be able to say that the measure of angle JKL is 90 degrees. And again, if they want to tell you, if I want to tell you, if anybody wants to tell you that lines are perpendicular, I should draw that little square in the corner. Anybody ever hear of complementary angles?
Isn't it an angle that's like on one side, it's on the other side too?
They share a side sometimes, but they don't have to. But frequently they share a side. And what's important is that it's two angles whose sum is 90 degrees. And so sometimes they share a side like this. They add to 90 degrees. Sometimes it might be, let's say this angle is 40 degrees and this angle is 50 degrees. Those would be complementary. It's important that it's two angles. If I just said it was angles whose sum is 90 degrees, I could picture three 30-degree angles. And that's not what I mean. It has to be two angles that add to 90 degrees. Is that vaguely familiar? If they're complements, they add to 90. And then can anybody guess what supplementary angles add to?
180.
Yep, so supplementary angles are two angles whose sum is 180 degrees. And so sometimes if we know that this is a straight line, then these two angles would be supplementary. They don't necessarily have to be sharing a side. If this angle were, let's say, 120 degrees and this angle were 60 degrees, they would also be supplementary. But again, when I talk about supplementary angles, it's got to be two angles. It's got to be a pair. And so if at some point in time on a test or quiz you're asked to do a definition, realize that it's important that you say it's two angles whose sum is that. Adjacent angles have the same vertex. They have a common side. But then they have no interior points in common. And so over here, I could say that angle 1 and angle 2, they have a common vertex, they have a common side, but they don't overlap. So angle 1 and angle 2 are adjacent. Instead, angle 1 would not be adjacent to angle XYZ because angle 1's on the inside of it. One can't be inside the other. They have to be next to each other with a common side and a common vertex. And oh heck, I wanted to go further than this. Am I going too slow for you folks with these definitions? Am I going too fast for you folks with these definitions? Or is this pacing all right?
All right.
I am going to stop sharing, stop recording.